Neptune sits 4.5 billion kilometers from the Sun, orbiting in the extreme isolation of the outer solar system. At this distance, sunlight is 900 times dimmer than what reaches Earth. These conditions should yield a quiet, geologically inert sphere of cold gas. Instead, Neptune hosts the fastest winds in the solar system. Supersonic storms the size of Earth rage across the planet at 2,100 kilometers per hour. This thermal budget highlights a massive energy deficit. Neptune radiates significantly more infrared energy back into space than it receives from the Sun. Uranus, Neptune's slightly larger twin, shares this environment. It sits tilted at 98 degrees, wrapped in a similar methane-rich atmosphere. These anomalous thermal emissions prove that surface weather is irrelevant. A massive, hidden thermodynamic engine must be operating deep within the planetary interior. The ice giant classification is deceptive. If you attempted to stand on these worlds, you would never find a solid frozen surface. The outer envelope consists primarily of hydrogen, helium, and methane gases. This cross-section shows the transition from the thin atmosphere into the mantle, a vast, churning ocean of highly pressurized fluids. Gravitational compression scales exponentially as you descend toward the core, subjecting the fluid to crushing pressures. In this environment, water and ammonia exist as superheated, highly compressed liquids rather than frozen solids. Identifying the internal heat source requires us to map the exact chemical behavior of matter under these extreme conditions. This diagram shows a methane molecule, one carbon bonded to 4 hydrogen atoms. These are stable in the upper atmosphere. But descending into the mantle, pressures hit millions of atmospheres and temperatures thousands of degrees. At this threshold, the methane is torn apart. The atoms separate, leaving free carbon floating within the high-pressure fluid. Thermodynamic laws dictate that atoms under millions of atmospheres of pressure must reorganize into their densest possible structural configuration. For carbon, this configuration is a rigid, three-dimensional crystalline lattice. This is the formation of diamond. Within this deep interior, diamonds are the unavoidable thermodynamic endpoint for atmospheric gas. Physicists faced a major empirical problem: how to verify a phase change occurring thousands of kilometers inside an unreachable planetary core. In 2017, researchers at the SLAC National Accelerator Laboratory utilized polystyrene plastic as a chemical proxy for the planet's methane. They fired a powerful optical laser at the target, inducing a massive shockwave, while precise X-ray pulses measured the material's atomic structure. The X-ray data provided conclusive proof. Diamond nanocrystals formed instantly within the material. A 2022 follow-up experiment added oxygen, yielding super-ionic water, a bizarre phase where oxygen solidifies while hydrogen flows as a liquid. Diamond precipitation is now an experimentally demonstrated physical reality. These laboratory results explain the thermal behavior of Neptune's massive fluid mantle. The newly crystallized diamond structures are significantly heavier than the surrounding slush of water and ammonia. This diagram illustrates the resulting mechanical action, a continuous precipitation of solid carbon sinking toward the planetary core. As millions of tons of diamonds sink, they convert gravitational potential energy into kinetic energy. The friction of this precipitation generates vast amounts of thermal energy, heating the surrounding mantle. Near the core, temperatures may rise high enough to melt these falling crystals into an ocean of liquid carbon. This planetary-scale mechanical process, falling rocks converting gravity to heat, powers Neptune's supersonic atmospheric storms. We can now scale our perspective from our local solar system out to the galaxy. This thermodynamic phase change represents a fundamental law of the universe. This comparative phase diagram tracks carbon behavior across different classes of celestial bodies. On the exoplanet 55 Cancri e, extreme compression creates a mantle composed primarily of diamond and silicon carbide. Even more extreme conditions exist in white dwarf stars like BPM 37093. As a dying white dwarf star cools, its ultra-dense carbon-oxygen core crystallizes into a single planet-sized diamond mass. Carbon crystallization is a strictly enforced thermodynamic law governing matter from gas giant mantles to dead stars. The breaking of molecular bonds under pressure initiates a journey that drives the generation of planetary-scale heat. On a cosmic scale, these crystals function as bulk mechanical components, dense weights utilized to power planetary heat engines. Mapping Neptune's interior establishes a direct, observable laboratory for the physical laws that shape the broader universe.